This weird concept that by our acts of observation we bring things into existence, at least in the realm of the very small, is supported by scientific experiment. Look at this. If you've ever seen a compact disc, a dragonfly's wing, or the colours on a soap bubble, you've witnessed interference at work. In each case, the colours you see come not from pigments, obviously no one's painted the bubble, but from optical interference. Light travels as indivisible packets of waves called photons. In a loose way of speaking, you can regard a photon as a fundamental particle of light because you cannot split it. It is a loose way of speaking because it also acts as a wave. In fact, each colour of light is carried by photons of a specific wavelength. Look at the soap bubble. Light is reflected off the outer and the inner surface of the soap film. Now, if that film is thin, as it usually is, photons with the right wavelength will reflect off the outer surface one way up and off the inner surface the other way up. The peaks of one photon wave coincide with the troughs of the other, so the wave disappears, and with it the photon. So a particular colour of photon won't get reflected at all. It gets cancelled out. So what began as white light, a mixture of every colour in the rainbow, now has an ingredient missing. The result is that the reflected colour is no longer white, it has a hue to it, hence the shimmering rainbow lines. Illuminate the bubble with monochromatic light, photons of one wavelength only, and as before, in some places on the bubble, the photons reflected off the outer and inner surfaces cancel out. But now, on these parts of the bubble, there's no light left at all. No more rainbow lines, they're just dark streaks. The photons are said to have interfered with each other. The particles of light have quite simply disappeared. Where have the photons gone? You can try to track them down by using a laser. Two screens, two mirrors, and a semi-silvered mirror acting as a beam splitter. The beam of photons from the laser is split in two by the semi-silvered mirror, and the other two mirrors make the beams cross through each other and hit the two screens. So half the photons take one path to one screen, half take the other path to the other screen. So far, so good. Put in the equivalent of the soap bubble, a second beam splitter just where the photon beams cross. Now the beams travelling to the screens are a mixture of photons from both paths, and we can position the beam splitter so that interference takes place. Because of the interference, one beam of photons cancel out, so the beam disappears. No photons at all hit the centre of one screen. The other two beams reinforce each other, so there's a bright patch in the middle of the left-hand screen. We've now set the stage for an experiment Professor Wheeler sees as crucial to the anthropic principle. What happens if we dim the beam so that only one photon at a time comes out? If the photon goes this way, the second beam splitter may send it to either screen. We can't tell in advance. If it goes the other way, the same applies. One thing's for sure. We can't possibly get any interference because there's no second photon to interfere with. So just as before, we'd expect a 50-50 split. Half the individual photons to go one way, half the other. Okay, let's do it. Turn the wick down. And what we find is each individual photon hits one screen only. None hit the other. Interference takes place even with one individual photon. What is each single photon interfering with? Itself? If so, each single indivisible photon must magically be going both ways through the apparatus at the same time.
We've all seen, I hope, the picture of the skier with his track going both ways around a tree, a clear impossibility. And so we would say likewise about the photon in the split beam experiment. How can it possibly go through the upper track and the lower track, both? It's nonsense, clearly. Bohr asked about it once. Where can the photon be said to be in his travel from the entrance to the reception? To be, he said. What does it mean to be? We have no right to speak of where the photon is, what it's doing. It's like a great smoky dragon. The tail is definite where it enters the equipment. The mouth is definite where it bites the observing device. But in between, it's nonsense to talk of what it's doing.
Niels Bohr's view was that the only way to give the photon's path any reality was to get in there and observe where it goes. And indeed, you can do that. The trouble is that you then destroy the original experiment. Now that only one photon beam hits the second beam splitter, there can be no interference. Photons come out of the beam splitter both ways. Conversely, with interference, you simply can't observe the photon as it crosses the apparatus. So, within the apparatus, the photon cannot be said to exist at all. That's why it's so difficult to say which way it goes.
You can't do away with the observer, and that's a fact. You may say, well, things may be a bit peculiar down among the atoms, but they're so small, who cares? When it comes to tables and chairs and people and everyday objects, these quantum effects are just insignificant. But you can't really get away with that, because after all, tables and chairs and people are actually made of atoms. These are quantum objects, and so ultimately we and everything else are quantum systems. And even though these quantum effects are very tiny, it's a little bit like the girl who gets pregnant and says, well, what are you worried about? It's only a little baby. It's an acute problem of principle.
A problem of principle that John Wheeler's met head-on. If we bring the tiny world of the quantum into existence by our observations, do we need any other mechanism to account for the whole of reality? The question seems ridiculous until you recall that the quantum reactions that produce the DNA molecule go on to produce the elephant, and that quantum events within the Big Bang gave rise to the entire material universe. The implications for the anthropic principle are astounding.
The strong anthropic principle states that the universe must give rise to life at some point in its course. Modern quantum theory, the overarching principle of 20th century physics, leads to quite a different view of reality. The view that man, or intelligent life, or communicating observer participators, are the whole means by which the very universe is created. Without them, nothing.
This revolutionary idea has been crystallized as the participatory anthropic principle. Frank Tipler.
The participatory anthropic principle says that the entire universe and everything inside it is brought into existence by innumerable acts of observation, by all the observers that have ever existed, exist now, or will ever exist.
Now, I don't agree with this view, but there is something very attractive about it. If it were true, we wouldn't need any other explanation for the whole creation of the universe. It would be observers that bring the universe into existence, not just in the present, but throughout the whole past, right back to the Big Bang.
But how can this be when no one was alive to observe the distant past of the universe? The mystery is resolved by an experiment by Dr. Alan Stockton, who used the University of Hawaii telescope to take a digital photograph of two quasars that lie very close together. Stockton thought these might actually be one quasar, whose light radiating in all directions was partly focused by an intervening galaxy to produce two images on Earth. But where was the galaxy? Stockton's team subtracted the left-hand image from the right-hand one, and, lo and behold, there was the galaxy. It's about a quarter of the way from us to the quasar, and it's bending light beams from the quasar that have spread apart by 50,000 light years, and it's brought them almost back together by the time they reach the Earth. So we see two images of the same quasar. Now, here's what scientists call a thought experiment. Go back to Wheeler's split beam apparatus, but now the source of light is that distant quasar. No need for a beam splitter. Each point on the quasar sends off light in all directions. The intervening galaxy plays the part of the two mirrors that bring the rays of light back together again. The rest of the apparatus is just as before. Night comes, and we find that the quasar is so faint that only one photon comes through every minute. Intuition tells us that thousands of millions of years ago, each photon chose one of two widely diverging routes to our apparatus because over a period of time, half hit one screen, half the other. Suddenly, we decide to put in the beam splitter to cause interference. Suddenly, every photon hits the left target. None hit the top one. What happens to all the photons already billions of years into their widely divergent journeys? There's only one answer, the one given by Bohr. The ancient light showing us the distant quasar didn't exist until we carried out our experiment. In other words, the quasar didn't exist billions of years ago until the first observers saw its light. And what applies to the quasar applies to every star in the universe, everything whose image takes time to reach us.
The nice thing about John Wheeler's participatory anthropic principle is that time isn't a barrier. When we look out in space, we look back in time. We see objects as they were a long time in the past. And if we see a photon from some distant quasar, say, then we're seeing something which was emitted before there was any life on Earth even. Now, the act of observation of the photon is, of course, central to projecting it into full reality. So it seems that our observations here and now have, in some backwards in time sense, an effect on the reality that was in the remote past.
We are participators in bringing into being not only the near and here, but the far away and long ago. We are, in this sense, participators in bringing about something of the universe in the distant past. And if we have one explanation for what's happening in the distant past, why should we need more?